accounting for the heat generation rate, and QR accounting for the convective heat removal, and its rate of disappearance by reaction. Rearranging the component balance gives the effluent propylene oxide concentration directly, dependent on reaction temperature because of the Arrhenius term, K of T. At low temperatures, the low rate of reaction leads to negligible heat generation. In contrast, at high temperatures, a high rate of heat generation is expected, with a value limited asymptotically by the supply of reagent. The heat removal rate is linearly dependent on the reaction temperature and the total material throughput, Q. To the energy balance is represented graphically as the intersection. A single solution occurs at an operating temperature of 110 degrees centigrade. This corresponds to a high temperature. Increasing the value of QW to 300 kilogram moles per hour again gives a single on the parametric plot also. Increasing QW to 350 kilogram moles per hour leads to also obtained for a water flow rate of 400 kilogram moles per hour. A further increase of QW to 450 kilogram moles per 350 kilogram moles per hour, in which only stable high temperature operation is possible, above water flow rates of about 450 kilogram moles per hour, in which only stable low temperature operation is possible, and the region in between these, in which solution explains the results that can be expected from the sensitivity analysis. High temperature steady state solution is obtained, jumping to the low temperature solution after passing through the multiplicity region. With decreasing values of water flow rate, the low temperature steady state solution is obtained, jumping to the high temperature solution after passing through the multiplicity. In the neighborhood of the multiplicity region is typical for CSTRs operating both adiabatic sensitivity analysis on an adiabatic CSTR for the hydrolysis of propylene oxide using HYSYS plant. To see a definition of the problem and the impact of water flow on the reactor performance, the feed is divided into two parts. The stream, feed 1, is defined, consisting of the propylene oxide and methanol components. After defining the stream name, feed pressure is set to 300 kilopascals and its temperature to 23.9 degrees centigrade. Propylene oxide and methanol are entered, noting that this stream does not include the water feed 1. We next introduce the stream water 1 at the same conditions as feed 1, containing only water. The initial molar flow rate is set to 160 kilogram moles per hour, pallet, and placed on the PFD. In the CSTR design connections page, the two previously defined feed streams, the vapor and liquid effluents. Since an adiabatic reactor is modeled, no energy stream need be attached. The reactions page, previously defined kinetic reaction available in the global reaction set is installed. It is noted that the reaction is moderately exothermic with a heat of reaction of 90,000 K. This prompts us that the reactor volume is unspecified. So returning to the design page, the total volume of the reactor vessel is defined as 2.2, where it is noted that in these conditions, the reagent is almost completely exhausted. The effluent temperature is computed as 110 degrees centigrade, which is identical to that estimated, theoretically, obtained as a function of the water flow rate. To do this, we invoke the HYSYS plant data book, whose usage is described in the link. The book variables for this problem are the molar flow rate of water 1 and the temperature of the liquid effluent stream, L1. In the case studies page, the molar flow of water 1 is set as the independent variable and the temperature of L1 as in the theoretical analysis. The sensitivity analysis will be carried out from 160 to 500 kilogram moles per hour at intervals of 10 kilogram moles per hour. Note that this case study is named forward, since it holds the results of the sensitivity analysis increasing water flow rates. The results of the sensitivity analysis indicate the jump in the operating temperature occurs at a water flow. As seen in the theoretical analysis, a distinct temp 1 is defined, with pressure and temperature set to the feed conditions and molar flow rate set to the upper value of 500 kilogram moles per hour. This stream is defined as consisting of water only. It is split using a T object to give two streams, temp 2 and water 2. The molar flow rate of temp 2 is set initially to 0, making the molar flow rate of the residual stream water 2 equal to the temp 2 is now an independent variable which, when increased from 0 to 342, consists of the propylene oxide and methanol components of the feed, and the reactor model is defined as before, with vapor and liquid. The data book, we add three new items to the variable list: the water 2 and temp 2 molar flow rates, and the temperature of stream L2. This page, a new case study is set up, named backward, in which the temp 2 molar flow rate is the independent variable, and the water 2 decreases with increasing temp 2 flow. We set temp 2 to vary between 0 and 340 to indicate a jump from the lower operating condition to the upper one at a value of temp 2 flow of about 150 kilogram moles per hour. Sensitivity analysis using the tabular option. The results from both forward and backward sensitivity analyses are even more conveniently exported and displayed using the graphics capability of MATLAB, as shown here.